So I recently came across a question in one of my problems for one of my classes, and it is to find the derivative of a function x to the n without using the power rule or just giving the answer. We all know it'll be x to the n minus 1 or n times x to the n minus 1. However, we want to derive that. So we know that for a derivative, the definition is the limit as h approaches 0 of f of x plus h minus f of x over h. Now, we can use this to our advantage. So, the derivative of x to the n is equivalent as saying limit as h. I'm going to use p instead, just so you could differentiate the difference between the p or the p and the n. So the limit as p approaches 0 of x plus p to the n minus x to the n, all of that over p. Now, knowing the binomial expansion, we know that any number x plus y to the nth power is equal to the summation of k, going from k equals 0 to 1, of n choose k times x times n minus k times y to the kth power. Now, plugging in each number, we know that limit as p approaches 0 of this, which I'll put in blue right here, n k equals 0 of n choose k x to the n minus kth power times p to the kth power. And then we'll put this in parentheses, minus x to the n, all this over p. And we know we can expand this out into its sum form, and we can get the limit as p approaches 0 of, we'll have the first term, which is x to the n, sorry, it is the limit as p approaches 0 of n choose 0 times x to the n p to the 0th plus n choose 1 times x to the n minus 1 p to the first plus n choose 2 times x to the n minus 2 times p squared plus dot dot dot. And then we're going to go all the way to the kth. Well, I'm not going to write that down because we're going to do some manipulation. And then minus x squared, sorry, not x squared, that'd be x to the n over p. Now we know that n choose 0 is just equal to 1, and p to the 0th power is equal to 1. So this n will end up canceling with this. So we'll end up with the limit as p approaches 0 of x, n choose 1 to the x to the 1, p1, p to the first, and then this. Notice that the rest of these will have a p to the something power. So we can take out a p from this, and I'm going to write this in yellow. We could take a p out of this and put it to the front, and I'm actually going to put brackets, and then n choose 1 times x to the n minus 1 will have nothing, and then plus n choose 2 x to the n minus 2 times p dot dot dot, and then we're going to have n choose k at the end, x to the n minus k times p to the k minus 1. And we're going to have that all over p. This should be a bracket. I messed up there. Now, we can cancel out this p and p, and then we're just going to end up with this over here. So we're going to have the limit as p approaches 0 of n choose 1 x to the n minus 1 plus n choose 2 x to the n minus 2 times p plus dot 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 plus n choose k, and I'm just going to write that because we know that it's over here. Now, we know that n choose 1, anything, any number choosing 1 is itself, so we know that this is just equal to m. And now we're going to plug in 0 to all the p's, which would end up this whole expression equaling to 0. Now, that just simply leaves us with the derivative of x to the nth power is equal to n to the x. Is equal to n times x to the n minus 1th power. And that is how you derive the power rule. A very simple, yet effective derivative rule. And there's a very simple way to figure it out. So yeah. Hope you find that a little bit helpful to help out the Calc 1 students specifically. If you don't know this, the binomial coefficient theorem. Yeah, the binomial coefficient theorem. You will learn this in either discrete or any proof class, or Calc 2 as well. I believe Calc 2, I could be mistaken, but I know in discrete you will cover it if you have time for it, which you most likely will. So yeah, with knowing a little bit of knowledge on discrete, you should be able to prove this just fine. And like I said, this came up with one of my problems, and I just wanted to show it with you because I found it really interesting to derive the power rule. So yeah, hope you enjoy that, and stay safe, stay positive. Peace.